This is a training session about accuracy and precision, a back to the basics version with a practical investigation. I understand that this can be somewhat complicated occasionally. However, we're going to try to break this down and use real-world data to help understand it. Why do we care? Well, evaluating the quality and accuracy is very important. It really isn't useful data if we don't know what accuracy is attached to it. And it's used for diverse applications, and then knowing how accurate the measurements are that we've used to derive this data. It could be life or death if it was, say, locating a gas pipeline or some mining operation. We also care because errors exist in any product we produce, no matter how accurate the instrument or process is that we utilize. It's because all measuring instruments are not perfect, including laser instruments. They may seem close to perfect, but they're not. We may also take the accuracy and precision for granted. Sometimes we just go about our day and take this for granted. And then finally, are we meeting the required accuracy standard? And throughout this presentation, we're going to talk about error values for least squares adjustments. This is a very valuable portion that will be threaded throughout this presentation. Finally, we need to design our projects based on error theory. Yes, design. You'll hear me talk often about us being professionals, and yes, we do design our surveys just like engineers and architects. With the least squares, an example here shows that you're going to either constrain or weight the original control points. Now, constrained means that you're going to just take them as the gospel, or that they're held without any error. Now, weighted means we would actually put the weighted error in it, and in reality, every control point does have error. And we would need to specify the confidence intervals. Most of the time, we are looking at 95% confidence level, and we're going to talk more about that later. So on the GNSS side of things, again, we can choose individual or use defaults. Now, individual means that the data attached to the equipment will come through in the software and populate the errors. Use defaults means we will plug in known or reliable values that we like. And then we would plug in for the total stations the standard deviations for things such as the horizontal angle, vertical angle, slope distance, absolute and relative, and then centering heights for the setup and the target. Very similar on the GNSS side. If we use defaults, we're going to do the absolute baseline and relative baseline, which we can get from data sheets, and then the centering height errors as well. Levels can be used with least squares also. The one we will focus on is the relative level line. Finally, the metrics in geospatial production process. For any geospatial data product, we need to collect some metrics such as the map fit, the coordinate system and datum, the geometric and or radiometric quality. How well do these metrics fit a standard is very important. We have some federal and we have some professional associations, as well as state-specific accuracy requirements that we need to meet. This is part one of accuracy and precision. We're going to cover definitions, statistics, and accuracy standards. Accuracy is the degree of conformity of the observations to the truth. Precision is the degree of conformity of the observations to one another. An error is the difference between the observed or calculated, in some cases, value and the truth. Some examples are here. We're going to go through these in much more detail. The most desirable result is this accurate and precise here. Now, error and residual gets a little complicated, so bear with me here. But error is the difference between the observed, calculated value and the truth. We just covered that, right? If that's error, then what is a residual? Errors are the deviations of the observations from the population mean, otherwise known as the truth, while the residuals are the deviations of the observations from the sample mean average. So basically, the errors are from the population and residuals are from the sample. Now, we will most likely and most commonly be using residuals because we only have a sample on our measurements. We never really have the population. An accuracy is a statistical error or disturbance in the amount by which an observation differs from its expected value or truth, and the latter being based on the whole population from which the standard unit was chosen randomly. And precision is a residual or fitting deviation, on the other hand, is an observable estimate of the unobservable statistical error of a sample. And note that because of the definition of the sample mean, the sum of the residuals within a random sample is necessarily or nearly zero. It's not always, but it's pretty close. But the bad news is that the residuals are not necessarily independent, and we need an independent accuracy. Statistical errors, on the other hand, they are independent, and their sum within the random sample is almost surely not zero because it has bias. If we don't know the truth, then what do we do? Well, in practical terms, we substitute the mean average or the known value for the truth, otherwise the expected value. It's a very key point right here because most of the time, this is what we're dealing with. We are substituting the mean. The problem is it's not independent. And so what are the possible implications? A single measurement could be completely wrong. We have no idea without redundancy. No redundancy, that's indeterminate. Not accurate, not precise, means a poor instrument and poor procedure. Not accurate but precise, it's an interesting situation because they're close together, but they have a bias between there and the target. Means a good instrument, poor procedure, has bias. Accurate and not precise. This is what I call the you get lucky scenario. You do a good procedure, but you have a poor instrument, but you come up with a good result. So if you took the average of all these, they would hit the bullseye. What we're searching for is accurate and precise. We're both end up causing you to hit the bullseye. Good instrument, good procedure, no bias. Little oversimplified, but this is the general concept. And in summary, again, we're looking for the accurate and precise, or the not precise, but ends up being accurate, and then the precise with a bias that we can fix. A little bit of a joke for this is a mathematician, a physicist, and statistician go hunting. They find a deer and take aim. The mathematician shoots and ends up shooting 10 meters to the left. The physicist shoots and he misses 10 meters to the right. The statistician goes wild, claiming that we have now hit the target. Hopefully you get that. Average of left to the right by the same distance ends up hitting the target. The types of error that we have, of course, we must minimize and or remove the error in the solution. The three types of error that we commonly talk about are gross errors or mistakes and blunders. A blunder is really not an error. It's a mistake resulting from carelessness or negligence, and they must be eliminated. Systematic errors are predictable. And those are kind of the ones we like because we can fix them due to the functional relationship. They can be minimized or removed. Random errors, not much we can do about. There's no control over it other than good procedures help us overcome that and redundancy. Let's take a closer look at each one of these. Gross errors are true mistakes or blunders, part and caused by the observer. I'm not going to read all these to you, but you can imagine you take a measurement incorrectly, you transpose values, use the wrong datum or coordinate system. But in general, all of these follow a general lack of good procedure and a lack of attention. That can get you fired. Gross error is eliminated by adherence to good procedure, and document your deviations. We talk about all the time whether or not we should keep a field book with the electronic world we live in. I believe that the field book should be a journal and definitely document deviations to the procedure so that everyone knows what happens. You can use simple geometric or algebraic checks like the n minus 2 times 180 degrees for the sum of the interior angles of a polygon, and the sum of the backsides equals sum of the foresides when leveling, and independent measurements to verify consistency. So check into an additional point, and then of course redundancy is our friend, especially when we're talking about least squares. Mistakes and blunders can't be tolerated. They must be isolated and removed if the survey is to be useful. Systematic error are the errors in measurements that may be expressed by some functional relationship, often referred to as constant error. It's always there. Some of that could be temperature, other atmospheric corrections, horizontal and vertical collimation errors on total stations, and prism constants, etc. And they can be detected and removed, so that is a favorable trait of this type of error. Again, looking over to the right, that's precise but not accurate, but that bias can be fixed. Now, random error, nothing we can do about it. It remains, though, after you remove the gross and systematic errors. Some characteristics are that the error is typically small, and you're just as likely to have a positive or a negative value, and that's one reason why they end up, the sum of them equals 0 or close to it. There's no direct functional relationship, so removal of it is impossible. We can just procedurally and statistically deal with it. It must be considered random, and all measurements are subject to this uncertainty. So how do we deal with it? Again, statistical properties. For example, we have a lot of random error here, but when you take the average of it, because we did a good procedure, we get the right answer. In simple sense, the probable or expected value for a series of measurements is the mean, just as we just spoke of. And normal distribution, which we're going to talk about more, defines the probability that a measurement will repeat itself. This is part 1 of accuracy and precision. We're going to cover definitions, statistics, and accuracy standards. Accuracy is the degree of conformity of the observations to the truth. Precision is the degree of conformity of the observations to one another. An error is the difference between the observed or calculated, in some cases, value and the truth. Some examples are here. We're going to go through these in much more detail. The most desirable result is this accurate and precise here. Now, error and residual gets a little complicated, so bear with me here. But error is the difference between the observed calculated value and the truth. We just covered that, right? If that's error, then what is a residual? Errors are the deviations of the observations from the population mean, otherwise known as the truth, while the residuals are the deviations of the observations from the sample mean average. So basically, the errors are from the population and residuals are from the sample. Now, we will most likely and most commonly be using residuals because we only have a sample on our measurements. We never really have the population. An accuracy is a statistical error or disturbance in the amount by which an observation differs from its expected value or truth, and the latter being based on the whole population from which the standard unit was chosen randomly. And precision is a residual or fitting deviation, on the other hand, is an observable estimate of the unobservable statistical error of a sample. And note that because of the definition of the sample mean, the sum of the residuals within a random sample is necessarily or nearly 0. It's not always, but it's pretty close. But the bad news is that the residuals are not necessarily independent, and we need an independent accuracy. Statistical errors, on the other hand, they are independent, and their sum within the random sample is almost surely not 0 because it has bias. If we don't know the truth, then what do we do? Well, in practical terms, we substitute the mean average or the known value for the truth, otherwise the expected value. It's a very key point right here, because most of the time, this is what we're dealing with. We are substituting the mean. The problem is it's not independent. And so what are the possible implications? A single measurement could be completely wrong. We have no idea without redundancy. No redundancy, that's indeterminate. Not accurate, not precise, means a poor instrument and poor procedure. Not accurate but precise, it's an interesting situation because they're close together, but they have a bias between there and the target. Means a good instrument, poor procedure, has bias. Accurate and not precise. This is what I call the you get lucky scenario. You do a good procedure, but you have a poor instrument, but you come up with a good result. So if you took the average of all these, they would hit the bullseye. What we're searching for is accurate and precise. We're both end up causing you to hit the bullseye. Good instrument, good procedure, no bias. Little oversimplified, but this is the general concept. And in summary, again, we're looking for the accurate and precise, or the not precise, but ends up being accurate. And then the precise with a bias that we can fix. A little bit of a joke for this is a mathematician, a physicist, and statistician go hunting. They find a deer and take aim. The mathematician shoots and ends up shooting 10 meters to the left. The physicist shoots and he misses 10 meters to the right. The statistician goes wild, claiming that we have now hit the target. Hopefully you get that. Average of left to the right by the same distance ends up hitting the target. So types of error that we have, of course, we must minimize and or remove the error in the solution. The three types of error that we commonly talk about are gross errors or mistakes and blunders. A blunder is really not an error. It's a mistake resulting from carelessness or negligence, and they must be eliminated. Systematic errors are predictable. And those are kind of the ones we like because we can fix them due to the functional relationship. They can be minimized or removed. Random errors, not much we can do about. There's no control over it other than good procedures help us overcome that, and redundancy. Let's take a closer look at each one of these. Gross errors are true mistakes or blunders, part and caused by the observer. I'm not going to read all these to you, but you can imagine you take a measurement incorrectly, you transpose values, use the wrong datum or coordinate system. But in general, all of these follow a general lack of good procedure and a lack of attention. That can get you fired. Gross error is eliminated by adherence to good procedure and document your deviations. We talk about all the time whether or not we should keep a field book with the electronic world we live in. I believe that the field book should be a journal and definitely document deviations to the procedure so that everyone knows what happens. You can use simple geometric or algebraic checks like the n minus 2 times 180 degrees for the sum of the interior angles of a polygon, and the sum of the backsides equals sum of the foresides when leveling, and independent measurements to verify consistency. So check into an additional point, and then of course redundancy is our friend, especially when we're talking about least squares. Mistakes and blunders can't be tolerated. They must be isolated and removed if the survey is to be useful. Systematic error are the errors in measurements that may be expressed by some functional relationship, often referred to as constant error. It's always there. Some of that could be temperature, other atmospheric corrections, horizontal and vertical collimation errors on total stations, and prism constants, etc. And they can be detected and removed, so that is a favorable trait of this type of error. Again, looking over to the right, that's precise but not accurate, but that bias can be fixed. A random error, nothing we can do about it. It remains, though, after you remove the gross and systematic errors. Some characteristics are that the error is typically small, and you're just as likely to have a positive or a negative value, and that's one reason why they end up, the sum of them equals 0 or close to it. There's no direct functional relationship, so removal of it is impossible. We can just procedurally and statistically deal with it. It must be considered random, and all measurements are subject to this uncertainty. So how do we deal with it? Again, statistical properties. For example, we have a lot of random error here, but when you take the average of it, because we did a good procedure, we get the right answer. In a simple sense, the probable or expected value for a series of measurements is the mean, just as we just spoke of. And normal distribution, which we're going to talk about more, defines the probability that a measurement will repeat itself. It was once said that there are 3 kinds of lies: lies, damn lies, and statistics. And this couldn't be more true, or I share this opinion. You can manipulate statistics to look different, and without understanding what's behind the statistics, it can be very misleading. To illustrate the difference, let's look at a nice example of some measurements: 3-inch, 2-inch, 1, 5, and 4. And this was measured as a sample of the population, not the population. So taking the average, just like normal, nothing fancy there, add them up, divide by number 5 is 3.0. And the range is the highest to the lowest, so 5 minus 1 is 4. Now we get into more of the statistics that we're not familiar with. The variance is the measure of spread of dispersion around the mean. It's the mean square of all the errors. So the population variance is the sum of the average minus the error divided by n. Now that's for the population. Now it's a little different for the sample. It's divided by n minus 1 to accommodate some of the bias of a smaller sample than the population. So our sample variance for this one was summed up over 5 minus 1 is 2.5 inches. So our average was 3, sample variance is 2.5. Now that's somewhat helpful, but we've got a weird unit here, inches squared. So we really like to use the standard deviation. So standard deviation is the square root of the variance, a measure of amount of variation of the values of a variable about its mean. So a low standard deviation indicates the values tend to be close to the mean, or also close to the expected value of the set, while a high standard deviation indicates that the values are spread out over a wider range. It's most commonly used in the determination of what constitutes an outlier or what does not. So this is a very useful survey tool. When we look at this, we look for the outliers, and it helps us remove whether it was a mistake or blunder or some extreme bias. The population formula, the sum of the squares divided by n. Now notice that there is a little different symbol here, that's mu. So this means the average of the population. And this means the average of the sample. If we do that, the standard deviation is 1.58 inches. Now let's take a look at this in relation to the normal curve. The mean was 3, the range was 4, the variance is 2.5, and the standard deviation is 1.58. One standard deviation means that it's within 68%, or 68% of the time the measurement will fall within this range. The average minus the standard deviation, average plus standard deviation. So the distance from here to here would be 1.58, and the distance from here to here would be 1.58. 2 standard deviations means we're within 95, and 3 standard deviations is 99.7. The normal distribution, a little illustration here, shows that the more measurements you take, the greater the chance that they will resemble this normal or bell curve. As you can see, you get up to 512 measurements, you can really see that curve. And that allows us to do a lot of statistics. Otherwise, real data doesn't look that clean, especially if you don't have that many observations. For example, the mean of this is 53.61 and the standard deviation error is 0.61. So our mean is right there, and the standard deviation, or 0.61 in either direction, is right there, and that's at 68%. A little more talk about those confidence levels. We start out with calculating one standard deviation, but we need that to be in the 95th percentile. So we have to multiply by almost 2. Now we say 2, but we really mean 2 sigma, which is a nominal 2, when we're really going to multiply by 1.9599. So we've got 1.58 at 1 sigma. Multiply that by the 1.9599, you get 3.098 or 3.1 at 2 sigma, and you get 4.74 at 3 sigma. But be careful, don't just take an error value and not consider the sigma, because you could look at this and think, well, this 4.7 is a really bad number. Well, that's at 3 sigma, so you're going to be at 97% of the 99% of the time. So really think about these when you're looking at error and defining accuracy. You might, like I just said, you might mistake a larger value for it being poor, but it might not be. Again, standard deviation, so we had 1.581, 68%, 3.09, 3.1, 2 standard deviations, and 4.74 at 3 standard deviations. The root mean square is not the standard deviation. They are different, and it's a little of a tough topic here. But the RMSE is computed, and it looks a lot like the standard deviation. It's more about what the data has in it, and you'll see that that's really bias is the difference. But the same formula as the standard deviation, the sum of the error squared over n, and the sum of the error squared over n minus 1, and both of them you take the square root of it. Just difference of population versus sample. So let's talk about some facts about the RMSE. It includes random and systematic errors. So here's a clue. And it reveals the biases because it has the systematic error in it. It does tell us how accurate the data is. So we can see the bias in this one here, right? We've kind of referred to this a couple times. It's precise, but not accurate, but we can see the bias. Now, facts about the standard deviation is it's only the random error. So it does not have the systematic errors. But it reflects only how precise the data is, and it does not tell us how accurate it is in the presence of biases. The only time that they equal each other is when you remove the bias. Otherwise, the RMSE, otherwise accuracy, equals the standard deviation of precision plus bias. Now, that's just a nominal formula. You don't really add them that same way. Here's a visual representation. I like this here because it gives me and can give you a way to visually recognize this. So here's our normal distribution. Standard deviation away from the mean in both directions. And it's based on the truth or expected or that average value. Now, we may have a known value or the truth, and so there's a bias in there. And if you take the RMSE or the standard deviation and deal with the RMSE, you can get to what the accuracy is. So let's take some of this. We've got, again, you don't just add the two together. Really, in statistics, this happens a lot, but you take the sigma squared plus the bias squared, and the square root of that would equal the RMSE. Let's look at some examples here. The blue curve has a really low standard deviation, so all the data falls really close to the mean. The red is a little bit worse, so it has a higher standard deviation, and the copper or brown has a really high standard deviation. Now, they all come up with the same answer. They mean out at 0, except for the green one, which has a bias in it, and it needs to be corrected. let's take our sample. We already calculated the RMSE of 1.581. Now, you're like, well, that's the same number we've got for standard deviation. Yes, that's because we did not have any bias in this one. So that's a little bit of a magic trick there. Here's how I calculated it. We took these values, took the average, calculated the residuals, and then summed the residuals and took the square root of them. What's interesting here is that these do, when you add up the algebraic sum, they equal 0. Now, in reality, a lot of samples will not end up being 0, but they will be close. And if they're not, then you have a problem. Let's deal with simple error propagation of a single observation. So this is sort of an algebraic sum. And where can that be? This is what you do to sum that, is that the standard deviation of y equals the sigma squared plus the sigma squared of all the single observations, and you take the square root. If all the error is the same, then it's just sigma times the square root of n. Let's take a look at an example. It's a really good one here, is that we got a level loop, and we go from benchmark 35 to 36. And by the time we do the backside, foresight, we have 8 measurements. And we are told that our rod reading is within 0.5 millimeter. So maybe we have a digital level and it's 0.5 millimeters. So we can use our formula here, since it's all the same. The 0.5 times square root of 8 is 1.41, is the error involved in that set of measurements. Now, really, and this has been tricky, we tend to not include the error of benchmark 35. But truthfully and realistically, there is an error in benchmark 35. So if we took that, then we sum the squares again. We take the 0.8 that was intrinsic to benchmark 35 plus the 1.41 squared square root, and you get 1.62. So really, it's not the sum of the two, it's the sum of the squares and the square root. So it's a little bit worse, 1.62, when you consider the original control. Now, propagated error as an average. This should be the surveyor's favorite, because this is very similar to measuring rounds or taking direct and reverse measurements. But if you have a series of averages, then you can do something similar to the previous slides, where we've got the error squared plus error squared, and this time we sum them up and divide by n. If they're all equal, then we got the sigma over the square root of n. Otherwise called the standard error of the mean. So here's the surveyor's example. If we read direct readings from I to j and I to k, and we have a 5-second total station, and the horizontal angle would be, of course, I to k minus I to j gives you that angle. And we have a 5-second measurement at the backside and the foresight. So pardon the squared here. 5 squared plus 5 squared square root is 7.07. Now, if you do an averaged angle set, we have done them twice, and that would be the 7.07 divided by the square root of 2, or 5. Notice accuracy is getting better because we did more measurements. And then if you did 2 averaged angle sets, then 7.07 divided by the square root of 4 is 3.54. This is how we can go from a 5-second total station to about a 4-second accuracy. And then finally, the accuracy standards that we're going to talk about is you can have some federal ones, and these are well-written but complicated publications from NMAS, NOAA Technical Memorandum 58, and the Geospatial Positioning Accuracy Standards Part 3 are the most common. And in professional associations, they're typically based on these federal regulations or guidelines, and some of those examples are ASPRS and ALTA. And then you may have state-specific, some surveyor laws or statutes, and then the Department of Transportation sometimes produces their own accuracy values. Just to talk a little bit about the digital standards. It's relevant in this time because there's a new revision that comes out in 2023, or came out in 2023. It's replacing the legacy map standards such as the 1990 standard based on paper. And we've graduated now to digital instead of paper, so we had to come up with a new standard. And it left us with unlimited horizontal and vertical accuracy classes, which is pretty nice, and a required number of spatial distribution checkpoints based on a project area. It tells you what it should be, and then it's sensor agnostic. So in the past, you really had to have a calibration and involve that in the accuracy calculations. And it's all metric, so you'll have to convert if you don't want to use metric. Let's take a look at this. The relative position precision means that the length of the semi-major axis expressed in feet of the error ellipse representing the uncertainty of the position on a monument or witness marking a boundary corner of the surveyed property. So it's relative to the position of the monument or witness marking an immediate adjacent boundary corner. And look, we'll see some familiar terms here. Standard deviation, 95% confidence level. And it says use least squares. It doesn't say use compass or Crandall's. It says use least squares. For any measurement technology or procedure used for these, it says use trained personnel, compensate for systematic errors, just like we spoke of, and use the appropriate error propagation and measurement design theory to control the random errors and reduce mistakes and blunders and adjust for the systematic error. So the ALTA standards take the error and statistical theory seriously, and we should too. What that standard says is that you have a 2 centimeter constant error plus 50 parts per million. So this is where we talk about state standards. Now, many states have their own standards, but many also refer to the NSPS model standards. In this case, you've got classifications of surveys that are urban, suburban, and rural, and they have these relative positional accuracies, much like the ALTA regulations, of 0.07 feet plus 50 parts per million, or 0.13 plus 100 parts per million, and 0.26 plus 200 parts per million for the rural, and this is at the 95% confidence level, or otherwise known as 2 sigma. Now let's talk about part 2, the survey considerations for total stations, the accessories, levels, GNSS equipment, control, economics, and revision, and then finally safeguards. We're going to start out here with the considerations for total stations, and we're going to be covering angular, EDM, tribrac, and accessories. The modern total station, well, let's take a look back in time. This is a wild T1, totally optical theodolite, mechanical instrument with a top-mounted EDM. You would put that on top of here. Man, we've come a long way. Look at this, what we have now, fully electronic robotic instruments, digital encoders, automatic target recognition, coaxial EDM, really important, infrared or reflectorless distances, cameras, and some have scanning capability and much more. Again, let's talk about the angular and the EDM distance. Basic total station requirements. In an ideal world, all total stations would meet the following requirements. So we're going to refer to this figure over here, but the line of sight, or Z to Z, is perpendicular to the tilting axis, which is K to K. The tilting axis is perpendicular to the vertical axis, VV, and the vertical standing axis, VV, is perfectly vertical. And if that's out of plumb, we're going to talk about how we fix that. And the vertical circle reading is precisely 0 at the zenith. So if this is plumb and this vertical axis are together, the zenith is 0. Instrument errors occur if the relationships above are not maintained. They'll never be perfect, but we have to maintain them. Line of sight error or collimation. So A is the tilting axis, B is the line perpendicular to the tilting axis. And C is the horizontal collimation error, which we talk about quite often, and we correct for that, or line of sight error. And then D is the line of sight. Vertical index error. So mechanical vertical axis of the instrument, also called the standing axis. So this is the standing axis. B is the axis perpendicular to the vertical axis, or the standing. And vertical equals 90-degree reading in a specific face. The vertical index error is D. So that's how much it would be out. And the tilting axis error. So the axis is perpendicular to the vertical axis. That is A. And B is the mechanical vertical axis. And C is the tilting axis error. So that's in the plane of the vertical axis. And then D is the tilting axis. So we've got a lot to look after here on a piece of equipment. We have to take it very serious. And how we take care of that is we run procedures that will compensate for those index errors. So A is the mechanical vertical axis of the instrument. B is the plumb line. So the two things do not match right now. We have to correct for that. And C is the longitudinal component of the index error. And D is the transverse component of the index error. So what we have to do is we have to make these two come together. So we measure that through a procedure and fix that with software. Let's take a look at the summary of the instrument errors. So we've talked about the line of sight, tilting, compensator index error, I and T, the vertical index error, ATR collimation, so a tracking error, and a coaxial camera collimation. So almost all of these affect in the horizontal except for the compensator index error, I, and the vertical index error. Affects vertical is the compensator index error, vertical index error, and the ATR collimation error, and the coaxial collimation error. Elimination with two-phase measurement, almost all of them except for the ATR. Now that's eliminations is a strong word that sort of doesn't completely eliminate, but it compensates for it. And then automatically corrected with proper adjustment. Now again, that's not 100% correction, but by applying some correction, you do compensate for a lot of these errors. Let's take a look at this total station line of equipment. And what I want to look at is the one that's 1.5 second compensator accuracy. So that falls in the 5 second total station. We could be looking at any one of these up here that are the 5 seconds. So all these models have 5 second. When should I check my total station? Well, instrument errors are set to 0 at time of manufacture, service, and calibration, but they change. So you should change that before first use, before every high precision survey, after rough or long transportation, after long working periods, long storage periods, temperature change, pressure change, and whatever else might feel like needs to have the total station checked. But don't neglect this. Do it. So the summary of the total station accuracy, I'm going to use 152 meters or 500 feet, which is a normal topo measurement. I'm going to do scenario 1 where we don't do the compensation and we take poor care of the instrument to show you how bad it could be. Then we're going to compensate for it and show what it'd be if you did direct and reverse double centering. Okay, again, 500 feet topo measurement or 152 meters. I went through and took all of the errors that we come up with in the angular. I used 152 meters or 1.5 meters for a height of instrument. And I took those accuracies from the spec sheets. And then I calculated the distances in the horizontal and the vertical that this could be off. Now again, remember, this is not compensating the factors. It's basically an optical theodolite with a top-mounted EDM. Now EDM considerations, most EDMs on total stations are coaxial. Eliminates parallax, which could cause issues, so that's good. We're going to look at standard measurements of the prism and reflectorless measurements. They have to be treated differently. They both use an EDM, and most of them currently use time of flight. So that means that it's a method that calculates the distance based on the time of light pulse, which is the speed of light, from the instrument to the object and back. So it leaves the instrument, hits the target, and comes back, measures that time, and calculates the distance. Some characteristics of time of flight is it's very fast. I shouldn't say very fast, it's just fast. Laser spot size is large. And the accuracy compared to other methods, it's the lowest of them. And measurement is not possible if the signal to noise ratio is too low. There's another version of method for measuring, and that's using the phase shift. And that bases distance on the phase shift between the emitted and reflected signal of full wavelengths. So you red one is either the emitted or the return, but either way, what you do is from peak to peak, there's a distance there. And that is what can be used to calculate the number of wavelengths that was between the instrument and a target, and they can calculate the distance. Characteristics takes a little bit longer time to measure, but it does have small laser spot, and it is the highest measurement accuracy. Now comes a new form, waveform digitizer. So waveform digitizer combines time of flight and phase shift technologies, where the distance is based on the time between start and stop of a pulse, which is digitized. I'm not exactly sure what that means, except that I think it sort of has the entire signal digitized from start to finish. But some nice characteristics. It's fast, small laser, high measurement accuracy, and then its biggest thing is it's very long ranges, and it's configurable. Again, what does waveform digitizer mean? Well, it's not a single shot technique. It's short pulses. So here's the start of a pulse, and the pulse gets smaller as farther it goes out. Sent from the sensor, which allows for required rapid multiple measurements. So you can send many pulses, and that's how you can take a lot of measurements. What's the benefit? Well, precise single measurements to a prism up to 10,000 meters. That's a crazy long distance. Precise single reflectorless 2,000 meters, which that's way longer than that 300 feet we used to have. Laser scan up to 1,000 points per second. Of course, site conditions would affect that. Now let's take a look at the EDM. So we were looking at angular, now we're looking at the EDM. Now there's a lot of information here, from using a single prism to no prism or any surface. So this is reflectorless down here. This is single prism, precise and fast, tracking, which you typically use in stakeout, averaging, and then long range mode. They all have different accuracies, all the way from 1 millimeter all the way up to 3 millimeters, and the parts per million, 1.5, looks like the highest one is still up. Nope, there we go. Long range is 5 millimeters, which is the highest constant error, and 2 parts per million. So it would make sense that your reflector or the long range would have the most error. Now, speaking of reflectorless, 2 millimeters plus 2 parts per million, or over 500 meters, 4 millimeters plus 2 parts per million. So again, long distance with this type of EDM. But look, they've all been described by parts per million. I know that can be a little confusing, so we're going to talk about that. All right, so this is a really nice diagram that explains parts per million. So if you have an error band of plus or minus 5, well, that's the constant error. And the proportional error gets bigger the longer it is. So 5 millimeters constant plus 5 parts per million. So for every million, it grows 5 times, or 5 parts. Similar, a 2 plus 2 in plus or minus 2 is a constant error, and the proportional error is on the top and bottom. So proportional errors are measured in parts per million. Here's a couple examples that all mean the same thing. They all mean 1 part per million. 1 meter per 1 million meters, 0.001 meters per 1,000 meters, and 1 millimeter per 1,000 meters. So there's lots of ways to say the same thing. Let's take a specific look at this precise and fast. So once and fast, 2 millimeters plus 1.5 parts per million. Accuracy then, let's take a mile shot. So let's look at the long distance of that. Still not long distance as far as what this considers long range. So we would have 2 millimeters of constant error. And if we take the 1.5 times a million times the 1,609 meters, we get the proportional error, or 0.0024 meters. That comes out to 0.0044 meters of uncertainty without refraction included. So that's approximately 0.014 feet. Not bad for that distance. Let's take a little closer look at a topographic measurement. So we know we're not really supposed to shoot past 500 feet or 152 meters. So again, we have the 2 millimeters of constant error, proportional 1.5 per million times 152 meters is 0.002. So we have 0.0022 of meters of uncertainty. And that is approximately 0.007 or less than 1/100th of a foot. Now the parts per million rule of thumb. Okay, for those old timers out there, maybe you remember this card that used to come with your instrument for your EDM. And you used to have to look up at the pressure and temperature and then follow these lines out there and find out where the parts per million were, and you had to plug that into your EDM. You don't have to do that anymore, but that was really covering the parts per million error. Now, some standard parts per million that we know out there, that it's 1 part per million per 2 degrees Fahrenheit change. So if we go from 40 degrees in the morning to 7 in the afternoon, we've changed 30 degrees. So 1 parts per million per 2 degrees, well, that is 0.00001 per 2 degrees. And we take that times the 30 it changed, and we have 0.00015 feet. And if we take that, that's the proportional part of 5,280 foot shot. So it's almost an inch. If we do that for a 500 foot shot, we're closer to about a 1/16th of an inch, or 0.0023. Now, 1 part per million for every elevation change, or every 90 feet of elevation change. So let's say you started at elevation 2,320 and you changed to 900 feet. So you moved 1,420 feet in elevation change. Well, we got the 1 part per million per 90 feet. Then we've got this ratio. I won't read all the zeros to you this time. Divided by 90 feet of elevation. Now we're going to take that ratio times how many feet of elevation change, the 1,420. And again, we have all these zeros and 1,578 feet. Or for a 1 mile shot, we're looking at 1 inch. And for a 500 foot shot, we're looking at about a 1/16th. So interestingly enough, this example was designed to show you just how much changes in 30 degrees and 1,420 elevation has the same effect on an EDM. Now we can summarize all this on the total station accuracy of the plus the EDM. So we had this earlier, this top part. Now we're adding the EDM. So again, I took these 2 millimeters plus 1.5 parts per million, and I'm using that topographic shot and the temperature change and pressure change. I've assumed that we're going to have that as something we're not compensating for right now. So remember, this is the kind of the poor procedure. And so we're going to add those up here in a little bit. I want to make sure There we go. Okay. Now, let's not neglect tripods. So why wouldn't he buy that new tripod? Well, this is worse than the old one. So you got this fancy piece of equipment, old rickety tripod. Well, you do need a nice tripod. There's a standard for it: heavier, lightweight. Things to consider: height stability, torsion rigidity, horizontal drift. Of course, you can't help some of that if you're set up on ice that's melting or freezing. Got a lot of different models here. And you're going to put a tri-brac on top of that tripod, right? So we're going to have things to look at. Of course, it's got 4 main functions: connect the instrument, secure the instrument to the tri-brac, enable leveling, and a stable platform over time. So things to consider for your tri-brac: the construction and weight. You want a good tri-brac. You want a good optical plummet. Maybe it's laser. And then we do have to deal with torsional rigidity, or hysteresis, I think is how you say that. So circular levels of Leica Geosystem tri-bracs are specified within 6 minutes in 2 millimeters. That means a tilt level plane of 6 minutes moves if the bubble moves 2 millimeters. That can add up pretty quick. So centering accuracy at about 1.5 meters of height is about 0.5 millimeters. Now, this is a little academic here. We're not going to read all this, but that torsional problem of hysteresis, well, as a instrument moves, it does get vibration. So we're going to measure the torsional rigidity of a tri-brac. That's the red line down here. And according to some research, I found that error is less than 0.3 seconds. But we're going to take it into account. Seems pretty negligible. Now we've got the height measurement. So at 1.5 meters, maybe we say we're 1.5 millimeters is what the best we can measure that to. Now let's add all those things together. We've went angular, EDM, tri-brac, and we take a measurement. So we've got our new horizontal and vertical errors here. We're looking at a subtotal of 0.00566 meters and 0.00420 meters. Otherwise, 200th and 100th. Accessories, are they part of the system? Well, of course, those materials matter, right? Don't want to be driving your fancy Formula One race car on wagon wheels, right? Of course not. All right, so the accuracy and precision of prisms, thing to consider are centering accuracy, the coatings affected, front surface reflection, glass quality, reflection beam deviation. Well, we tend to maybe take these things for granted, but it does matter, right? I mean, a signal's generated, follows a signal path, it's reflected through the prism and back. It's going through beam divergence, an atmosphere, and then it's reflecting through the reflector. So a lot of prisms come with their centering accuracy already calculated. We go from a really low one here of 0.3 millimeters to up to 2 millimeters for a 360 prism. We're going to use the 360 prism because that's what we would probably be using with a robotic total station and taking 500-foot topo measurements. So how far out can a pole be? Well, it's kind of shocking, but we got 6 minute, 20 minute, 40 minute, 60 minute. I tend to use this 20-minute pole, but let's take a look at the most accurate one. And if you're out 1 unit of that, the 6 minutes, you're 100th out horizontally. Now, this is the common one that we mostly all have, the 20-minute. Well, that equals 400ths of a foot. So even with some pretty good poles, it doesn't take much to be out, right? Okay, now we're adding the accessories in. So we had the total station angular, EDM, tri-brac, taking a measurement. We have the prism and the range pole, and we've added those kind of accuracies in right here for horizontal and vertical. Now we got a little bit bigger numbers down here, and we're looking at 200ths and 200ths which is kind of what we would expect. Maybe vertical to be a little worse if we had a larger vertical angle. And speaking of such a thing, now we've got the measurement of a horizontal and vertical angle. And when you add those up, yes, we have a little bit worse in the vertical at 300ths and 200ths in the horizontal. So this is if we didn't take good care, we didn't compensate, we didn't plug in temperature and pressure and all those good things. We didn't let the instrument acclimate, all kinds of things like that. Now let's take a look. Does that example that we didn't take good care of, does that meet the ALTA standards? And we know that that is the maximum allowable relative positional precision is 2 centimeters of constant air plus 50 parts per million. It's based on the direct distance between two corners. So we're going to come up with a distance for these two corners. Accuracy then of a 500-foot line. So that's a property that two adjacent corners are 500 feet apart. 2 millimeters of constant air, 50 parts per million times 152 meters, 0.0076. So we have 0.0276 max relative positional error. Now we have to do our linear proportioning of error. So we take that number squared plus that same number squared, take square root 0.0104 meters. Now, we have 0.0104 meters, which is less than the 0.0276 meters. So we do meet the standard. Pretty cool, huh? All right, so if we backed up here, right here we calculated the maximum allowed, and we used the horizontal up here. Now we had 2 points, so this is why we did this 1 point and second point, and that's how we came up with this number and checked it against the maximum allowed, and we're doing okay. So here it is all. Now we're going to compensate. So a lot of these things disappear. They went to zeros. Now, it's not always going to be zero, right? You're going to have some error in there, but we're going to pretend that all of them have been compensated for. That's why all these zeros are in here. And now we're down to something we normally would expect. Just a little short of 200ths in the horizontal and about 300ths in the vertical. And again, this was for a 500-foot topo shot. This is the reason why we don't go past 500 feet. This is about all we care to tolerate when we're doing a topographic survey with a total station or a robot. Now we can sum up all the total station accuracy, again, of that topo measurement. And we did scenario 1, where it barely met the standard. We did scenario 2, and we definitely met the standard. As we spoke of, we're going to fill in some least squares numbers as we go along. So total station accuracy information depends on accuracy of total station. We picked a 5-second one, depends on the EDM. And we're going to say we have a range pole and we're using a circular prism. So what does that do? Well, we would fill all these in over here. We had the 5-second total station for horizontal and vertical. We had the parts per million, 2 millimeters, and 1.5 parts per million. That's the EDM portion. Now we have all these centering errors. And so we have a setup centering error, we have a target centering error, setup height error, and target height error of about 1.5 millimeters. These all we calculated in the previous slides. So now we're able to plug in what our starting standard deviations would be if we were going to do a least squares adjustment. If you want to learn more about that, here's where you can go, and you've got a lot of white papers that you can go read if you want to kind of dive into this stuff. Now let's take a look at the accuracy and precision of modern levels. Well, we have some specs and procedures on digital leveling standards. Set standard for digital leveling projects, accuracy classes, and periodically updated as knowledge and systems mature. So here's an example over here. of different class orders. Now let's take a look at the instrument itself. So we have a vertical axis tilt that we have to worry about. So this is the axis, this is plumb, and they don't line up, and they never will perfectly line up, but we can adjust to get as close as we can. So there's always still an amount of small tilt remaining after the instrument is leveled. So the compensator corrects for this error. So it detects what plumb is and fixes it. We have to do a check and adjust just like you would do for a total station that corrects for this line of sight error. The line of sight error expressed in arc seconds, about 1 second, is 0.1 millimeters in 20 meters. Not much. It's a warning if distances are incorrect in the check and adjust. Electronic line of sight error is now set as the correction, and values set to mechanical line of sight is also provided when you do a check and adjust. Let's take a look at some digital levels, an LS10 and a 15. And we'll look at the accuracies using an INVAR staff rod or standard rod. You can get down to 0.3 millimeters and 0.2 and 0.3. Those are some crazy good accuracies. Now, you got to look at what they mean. This is standard deviation, 1 kilometer double run, and it meets this ISO standard. Now, how we check and adjust some of that is we got 4 different methods, but the one we typically use is where you set up evenly between 2 rods, and then you move closer to 1, and then you can calculate what you need to adjust. And again, you can still plug in least squares numbers for a level if you're going to adjust that in a total network. Again, that depends on the accuracy of the level and of the pole. So we're going to say that we're using INVAR, and it's this really accurate one of 0.02 millimeters. Well, so what we do is, now again, because it's an ISO standard and it means relative level line, that's 0.0002 meters per kilometer ran of level loop. Now let's move on to considerations for GNSS equipment: rapid static, real-time kinematic, traditional basin rover, and then real-time kinematic networks. We're going to look at the Leica GS18 with a baseline length of 40 kilometers, or about 25 miles. Now we're going to look at static and rapid static first. So static is 3 millimeters plus 0.5 parts per million, and rapid static is 5 millimeters with 0.5 parts per million. So if we add those up, we got this baseline error, we got a tribrac and pole error, depending on which one we're using, and then we have a measurement of the height of the instrument. So again, we're using 40 kilometers. We've got our baseline distance errors in here for the vectors. And if you calculate all this out, you end up with 0.02305 meters, 0.02504, or 0.08 pretty much feet, and then similar on the vertical. Now let's take a look at real-time kinematic single baseline. Again, 8 millimeters plus 1 for the horizontal and 15 plus 1 for the vertical. If you plug those in down here, again, very similar, except now we're using a 10 kilometer, because you're not really probably going to go past 6 miles with a traditional basin rover, right? And we have these different accuracies for the real-time kinematic vector. Plug all those in, come down to 0.01806 horizontal and 0.02504 vertical, and so about 600ths and 800ths horizontally and vertically respectively. Now let's take it real-time kinematic network, and we're somewhere between the 40 kilometers and the 10. We're setting at about 20. So we've got a slope distance here about 20 kilometers. That's this longest baseline to some of my shots here. All right, so now we're going to look at the network RTK accuracies. Horizontally 8 and 0.5, vertical 15 and 0.5. We're going to come down here again with the RTK in baseline, and we're going to plug in those vector constant error and parts per million for 20-kilometer baseline, tri-brac, and a measurement of the height of the receiver. And you end up with 0.018 and 0.025 or 600ths and 800ths for using a network RTK with a baseline of 20 kilometers. Now let's see if this example meets ALTA, because we want to use real-time kinematic networks on ALTA surveys, right? Okay, so we start out with that error we landed on, 0.01806 and 0.02504. And that maximum allowable is 2 centimeters plus 50 parts per million. All right, so again, we have to sum the standard deviation errors to get the root mean square. So we take this 0.01806 squared plus that, because we've got 2 measurements, right? Measure 1 point, measure another point. We come up with 0.0255. Now let's see how this all works. Then if we're going to shoot a 500-foot line between property corners, 2 millimeters constant error, 50 parts per million over 152 meters, 0.0076, and this number we've had before, 0.0276 meters, is the maximum allowed. So 0.0255 barely meets the standard, just barely. So using RTK is a little concerning depending on how far you have between your property corners. Continuing on, now, if you have lines longer than that 152 meters or 500 feet, then you probably need to measure the points twice, and here's how that works. So if we have 2 measurements, the formula for that is that standard deviation, or that error we had horizontally, 0.01806, and now we have measuring a single point twice, right? Divided by the square root of 2, 0.01277. Now the accuracy between those 2 points is we have to take this, because we've shot up a point twice, and we're doing this on 2 points. So 0.1, 0.2, and we plug in that RMSE between 2 measurements, and we get 0.01806. So if we solve for the longest possible line using the 2 millimeters constant plus 50 parts per million times some distance, we can't go past this here if we measure twice. But we want to know how far apart some property corners could be if that's what we were going to do, is take 2 measurements on the same point and they be 500 feet apart. So you can be 321 meters or a little over 1,000 feet apart if you use real-time kinematic network and you measure each point twice. So be careful about that distance between the property corners. Let's take a look at summing all these up, the GNSS accuracy summary, because it's kind of interesting. We've got the 3 methods here, and we've got a baseline length of 10 kilometers, 20, and 40. So of course, for rapid static, we can go farther. Real-time kinematic network, we can go pretty far. And the closest one between baseline and rover is going to be traditional RTK. Well, even though the baseline distance doubled, because of the parts per million in our specs, they come out with the same horizontal accuracy and the same vertical accuracy. Now that falls for all of them. So interesting enough, that's even at a 40-kilometer baseline. Because of the static parts per million and constant error, all these different baseline lengths come out to be a very similar, the same vertical error, and the 10 and 20 come out to be the same horizontal error. Why is that? Again, that is because of the 8 millimeters, 15, 8, and 15, plus the parts per million, Well, that horizontal parts per million is 1, and the horizontal of the network RTK is 0.5, 1 and 0.5 here. And then static with long versus rapid static, of course, we've got 0.1 parts per million starting at 3 millimeters and 3.5 with 0.4. So it's because of these numbers here is why we end up with these same numbers up here. The least squares estimates for GNSS, well, it's going to depend on the accuracy method. So let's look at rapid static first. And then we have a tribrac. So we look at, again, I'm going to back up here, but we're going to look at the rapid static method. And it depends on the accuracy of the GNSS. And we're going to say we have a tribrac because we're doing rapid static. Take a look what we would fill in here. Well, remember rapid static from the specs, we would have an absolute and relative. So we have 3 millimeters constant error and 0.5 parts per million baseline relative error. And then centering errors for the reference, well, we're going to say that in a static one that we're going to have 0 for one of the bases. And then rover about 1 millimeter. And for the reference height errors, we're going to say, again, maybe we're coming from a core station and downloading directly Rhinex files from it. You might have some error here if you're using a traditional base and rover, but that's not what we're doing. We're doing static. And then rover height errors of 1.5 millimeters. Now let's combine total stations and GNSS where it gets kind of interesting. So this is a point we set with GNSS and another point here, and they have different errors resulting. So we're going to look at what would happen if we set up on these two with a total station or a robot. We're going to look at I like to look at the worst case scenario. So if I back up to that worst case scenario, you set on this point and you happen to get the worst of it, which typically happens to us. So we kind of get almost the maximum error here, and we backside and we get the maximum error here. So we're ending up getting the worst of both ends of that line. The best scenario is where you call this point good and you backside this point and you've still got that error built in it. So you have some angular error based on, again, these spec standards. This is how bad things can get. So if you have the distance here between a pair of points, that's what we're looking at, a pair of points. So distance here between them, and then how many arc seconds they can be out. Short distance is bad news. 10 meters between. Worst case scenario we looked at, 412 seconds out. Best case scenario, 103 seconds out. Now, you'd run that same thing out to 1,000 meters, you got 4 seconds and 1 second. So this is why we don't like points really close together when we do a pair of real-time kinematic measurements. I like to come up with the practical scenario, which is where we actually pick this point for a hold of the northing and easting, and we say our backside is sort of the gospel for our backside azimuth. If you do that, then at least you're not adding this error back into this one because you're saying it is just the azimuth mark per se. Now let's talk about principles of survey control. Historically, you would find all available horizontal vertical control, observe and monument a primary control network, and observe secondary order traverses inside, and even third order as needed. And then you'd start surveying and stake it out. Well, in today's world, we got to think about things differently. Are we using GNSS or a total station? And should I perform basic RTK, real-time kinematic network, or rapid static? And will I be able to use Opus? Is there an RTK network available? How long and how many times should I occupy a point? And can I just work on a local grid or state plane, or we have the new state plane, low distortion projections? And can we be modified state plane to the ground? A traverse adjustment nowadays, instead of doing compass and crandles, which would be traditional. You're probably going to do least squares. And if you're going to do that, you are going to think about attacking the control differently. In the past, you just would have traversed around the perimeter. Well, that's still the case, but you're going to need to do cross ties. And the more cross ties, the better the strength of this figure. And that will help with a least squares adjustment. Yes, it is more work, but some regs, like Alta, require you to do a least squares adjustment. Again, control today. What control should I look for? Can I use NGS data? And why do I get a bust when my base is set up on a HARN station? I check into another HARN close to my job. Well, we'll talk about that. And then also, why do I get a bust when I set my total station up on 2 GNSS RTK points? Well, we kind of just looked at that, right? Well, one reason we could have a problem between HARN points is maybe we picked up an old coordinate instead of paying attention to the NGS data sheet. There's superseded control, and these numbers are different than the ones that are currently adjusted. And if you did use the wrong ones, we've done a little math here to show you just how bad it could be. And we're talking not terrible, but not great. In the longitude, you're 100th out. Or you're 0 seconds and 0.01 seconds. And the difference out here is 0.002 seconds. So it can start to mount up. In real terms, these were arc-second differences. Okay, so this turns out to be almost 2/100ths in latitude and 1/1400ths of a foot in longitude. So while these numbers don't seem like much, they turn into quite a bit in real terms on the ground. And we this by assuming that 1 second of arc is approximately 100 feet. Now let's talk about NGS control, another possible reason for a bust. Well, are you using control from the same adjustment, from the same epoch, or epoch as some like to say? Have you taken into account the monument velocity over time? That happens a lot in states like California, some in Arizona. What's the accuracy of my point? Is it local or network accuracy? And have I considered geoid residuals? And am I using the correct scale factors? Grid scale, elevation scale factor, and combined scale factor. Economics of accuracy, because time is money, right? So we have to balance what the customer wants versus what they need. And do we have the logistical resources to accomplish it, the right equipment? When does it need to be completed, and what will that cost? So the result is a professionally designed survey that meets the job requirements or specs. And you'll hear me talk a lot about us professional surveyors. We are designers. We do design a survey to meet the requirements. Unfortunately, you probably have seen this where you can only pick two, good and fast and cheap, and good and cheap, but all of those three doesn't exist. So we have to take all these things into consideration and make the right professional choices, or we can go broke by kind of overdoing the accuracy thing. We want to avoid revision, right? So how can we use the same data points on future projects? What are the best locations for the base stations so that you don't have to move them or set new ones? Can my total station control points be used for GNSS and vice versa? Are the marks permanent or temporary? And can anyone retrace my steps? So just like land surveying of boundaries, we need to provide metadata or notes on plats to let people know what scale factors you've used, what coordinate system, what datums is all very important to avoid having to revise your survey. Safeguarding. So care of equipment, independent checks, redundancy, follow procedures, backup raw data daily, maybe sometimes even more. Maintain the integrity of the raw data, which Leica is really good at that. Do not let you edit some things to keep that integrity. Maybe some new technology, though, can help us mitigate or minimize some mistakes and blunders and errors that can happen from using this equipment. Care of instrument or minimizing the errors. Well, I won't read all these to you, but you should know most of the care you should take. You keep them in a case, avoid scratching the prisms, Maintain a good tribrac. Use tripods for the intended purpose. So you got a lot of examples here. Don't use tool for the wrong reason. Don't use your tripod as a hammer. Take care of this equipment. It costs a lot of money, and it can handle some abuse, but not a lot. Because a big mistake is not taking care of that range pole. Yeah, this got my friend fired, but this actually happened on a job of mine where a guy couldn't turn the angles within 4 seconds, so he couldn't double center within 4 seconds. So he would take the range pole with a prism and throw it like a javelin. And you definitely better not do it with this AP20 IMU on the side, on the end. Yeah, and he got fired. Part 3, new technology. So let's take a look at some of the new technology and the accuracy and precision involved in them, and let's see if they can help us out. We're going to cover total stations and some new functions, multi-stations or robotic stations and new functions, and GNSS with a few new functions. Total stations with auto height of instrument, and also total and multi and robotic stations that take images, very common nowadays. Let's take a look at the specs here. So the auto height has an accuracy for it, of a distance accuracy of 1 millimeter at 1 sigma. And then we're going to look at this total station here at the end, the TS10. And so 1 millimeter at 1.9599, because remember, this is 1 sigma. We're doing everything to the 95th confidence level, 95th% confidence level. So you need to take that times almost 2. So we have 1.9599 millimeters to be at 2 sigma. And what's that do for us on the auto height? Let's say we have 1.56 meters. Well, what's neat is there's some functionality in this new equipment where you can hit measure height and it does it for you. If there's a height offset, you can have that built in, take the measurement, and it'll calculate the total measurement height without having to go to the side and having an angle and built-in inaccuracy. And then that plugs it in for the instrument height. Very quick, very nice, saves time, saves errors. Now on the imaging side, this is pretty neat. So these instruments have cameras built into them. And this one, in this case, has a 5 megapixel CMOS sensor. Again, using the TS10. Now, imaging comes with what's called a mounting error. So an image plane rotation and tilting, similar to our total stations tilting on the axes. But if both the horizontal and vertical components of the coaxial error are assumed to be 2 seconds, and the elevation angle is 50 degrees. So this is what we're going to use as an example. This came from a study, Zhang 2022. The errors of the horizontal and vertical angles can reach 3 seconds and 2 seconds respectively. So we will use that when we plug it into the spreadsheet. Now, let's take a look at the multi and robotics total stations. We have things as automatic target recognition, power search and filter, new EDM technology that we've talked about, target ID, pole height update, and tilt compensation. Lots of new technology lately. All right, so we do have to worry about a collimation error of the prism. I'm not going to read all these axes to you, but basically, this is where you're looking here, and there's an offset that we have to compensate for. That automatic aiming may be looking here and it needs to be here, so we need to compensate for that. Take a look at the MS60 multi-station. So the accuracy of the ATR plus, so the automatic target recognition plus methodology is 1 second. Typically takes 2.5 seconds to take that measurement, but 1 second. Now we also have some functionality called a power search and filter. By sending out a vertical laser fan, the instrument rapidly turns through 360 degrees, scanning for targets. And then using the power search filter, the instrument learns the location of these unwanted targets from that initial scan and then adds the real ones to the filter and excludes the bad ones. This doesn't work on accuracy and precision, but remember, we have the mistakes and blunders errors. So that will help out with that. There's a really cool video you can watch. But basically, these reflective items here, let's say you don't want that one, but you're working on this prism pole. So it will eliminate all those and only use this one. Pretty neat technology to keep you from making a mistake and blunder. Now the distance measure of the EDM using the waveform technology. Look at these distances. For a prism, 1.5 meters to 10,000 meters. We're only looking at 1 millimeter plus 1.5 parts per million. And into any surface up to 2,000 meters at 2 and 2. Again, the technology of waveform digitizing. So let's see, accuracy then of this 500 foot or 152 meter EDM measurement. Constant error, 1 millimeter. And now we got the 1.5 parts per million times the 152 meters. And we have 0.0012 meters of uncertainty, or well less than a hundredth at that 500 feet using this new technology. So we've made some serious strides in EDM accuracy by using the waveform digitizer. Some other new technology that helps you, again, eliminate, minimize mistakes and blunders is we have an IMU on a pole that lets you hold the pole not plumb. Very cool technology that also lets you get into some areas that you can't normally get in, like say underneath a car. And then we have auto target height. So this eliminates you putting in the wrong target height. The pole sends a signal to the instrument that tells it what the height is. And we have target ID that will not lock onto the wrong target. So again, not accuracy and precision, but it is eliminating and minimizing the mistakes and blunder errors. So we've got mitigation of that using the AP20. So the AP20 here functions as this tilt, and then the pole has that height measurement and the target ID. That's all part of the AP20 functionality. So the pole can be held at an angle, easily up to 30 degrees. And then you can have this at 2 or 1.6 or 1.8, whatever the pole says, and that will broadcast that signal to it, to the instrument, so that you have the right height and the right ID. So this knows that you're only looking at this pole and only this ID. Take a quick look at what this means. Pretty neat functionality, huh? All right, now back to accuracy and precision of the target ID. Again, identifies your target on the fly, and this prevents the locking onto other targets. Important when there's several surveyors, like shown up here, and again, prevents mistakes and blunders, and there's a video to show how that works. That auto pole target height, update the height for you automatically, again, prevents mistakes and blunders when you've had to change the height of the pole in different locations. An auto pole height is being, as we mentioned, it snaps into a position and transmits the information to the total station and or data collector. Tilt compensation, removes the need to level the pole. So the tilt compensation feature allows point measurements with an arbitrarily aligned pole, or you can hold it level and sort of proves whether or not you held it level or not. But again, prevents mistakes and blunders. And that tilt compensation, though, so what all that was to lead us to looking at the accuracy and precision of that. Well, at a target height of 1.6 meters, it's 3 millimeters plus 0.6 millimeters per degree of tilt for horizontal, and 1 millimeter plus 0.05 millimeters per degree of tilt vertical. If you went to the 2 meters, things are a little worse, so we recommend that you go lower to the 1.6 meters. All right, now, remember when we did this earlier with the total station, right? So we've got all these errors that we compensated for. Most of them are zeros. Tribrac measure, prism pole with accessories, range pole, prism and range pole, took a measurement, and now we've had to eliminate this single prism, the EDM part here. Because we have different accuracies that we're going to have to deal with, and that height of instrument. So how is this affected? Well, if you come in here and we do the new technology, right? So we have the auto height of the instrument, and let's say it's only 1 millimeter is what this told us at 1.5 meters height. If we use the imaging, we had that 3 seconds and 2 seconds. Auto target recognition. So now we've at 152 feet, we have some values here at 1 second. And power search and filter, coaxial collimation, we're going to assume that we've adjusted that out. Single prism averaging, that 1 millimeter. Now here comes the AP20 here at the bottom. Target ID and auto target height. Target ID doesn't affect it. Auto target height is 0.00196. Tilt compensation horizontally and vertically. I'm going to say we're going out to 45 degrees, so even a little bit past what we say is normal at 30. And you end up with these kind of errors. Sum them all up, and you have 0.03 meters and 0.009 meters vertically, or a tenth horizontally and 3/100 vertically. Now, I know that bucks things a little bit, but that's the way the predicted error works out. Doesn't mean it's going to come out that way when we really do it. We have the same functionality in the GNSS equipment. So tilt compensation and images. So this is based on a fusion of the IMU and GNSS, where the one previously was using the robotic portion of the instrument plus the IMU in the AP20. So the example of this is a GS18T for tilt. It's also immune to magnetic disturbances and works without calibration, fights multipath. You got the flexibility to measure the points with a leveled pole and still save the tilt values, which I mentioned with the AP20. But this, if you told your surveyors to make sure and be plumb, you can check them out because those are shown in infinity when you're done. But look, here's a great example. You need that corner. You can't get it with GNSS. You'd have to set up points, get the total station or robot out and survey that, or you're going to try to get in line and measure a distance and introduce some error that you don't have to. So let's take a look at the accuracies for the GNSS with tilt. So we have to add, now we had the RTK network accuracy right here. We have to add a horizontal uncertainty. So we have to add 5 millimeters plus 0.5 millimeters per degree of tilt down to 30. And now it makes me think of a mistake I mentioned. The AP20 is not limited to 30 degrees. It can be turned upside down and used for measurement because it doesn't need GNSS, right? So let me make sure I've clarified that. So GNSS, you still have to see antenna, see the satellites, where the AP20, you're not using GNSS. So we need to plug in this tilt compensation. The additional error is added here. And we're looking at 0.025 meters horizontal and 0.03 meters vertically. Now we're looking at something that's we're kind of used to, 0.08 horizontal and a tenth vertical. Now let's take a look at the imaging on the GNSS unit. So very similar to the robotic total stations and advanced total stations. You can take images. So you can walk with the pole and there's a camera on the side and you can take pictures of objects or stockpiles or whatever, and then you can create point clouds or create discrete points by using photogrammetry and measuring in multiple images these points you see here. Really cool technology. Okay, but there's error involved in an image point measurement. So one-click measurement in field and office, typically 2 to 4 centimeters. So, that sounds like a lot. So you have to keep in mind what you're using this for, right? Maybe some things it doesn't work on and some things it does. And that's at a distance from 2 to 10 meters. So you can't go out very far, but that's okay because you want to keep the images crisp and clean anyway. So you want to stay 2 to 10 meters. And if you use that, we're talking about 0.03 meters. I've taken the average between 2 and 4. I'm saying 3 centimeters. Now, remember earlier we had the GNSS unit with all its errors. Now we're going to add new technology. So we've had the tilt compensation because it's going to be tilting most likely when you take those pictures. We still have that in there. And then one measured point, 2 to 10 meters, and we're going to have it at the 3 centimeter level. So we jump out to 0.036 meters and 0.040 meters, or 1200ths and 1300ths, which it's not bad. That's not much worse than a GNSS RTK measurement. So if you need that kind of accuracy, then you can use this GNSS imaging. And if you want to learn more about that, there's a lot of white papers out there. You can go to the Leica Geosystems website and look up white papers in the search. So we covered a lot today, 3 parts: definitions and statistics of accuracy and precision. We went over some accuracy standards. We did survey considerations and looked at the accuracy and precision of surveying equipment, control, economy, and avoiding revision, and then safeguards for taking care of the equipment. And in my favorite part, where we covered the new technology that we saw definitely helps you mitigate errors and blunders, or mistakes and blunders, and then can also help you reduce some of the errors once you take into account the accuracy and precision. So the leave behinds for this presentation, of course, I hope you got a few nuggets out of this sometimes difficult subject matter. Accuracy and precision is kind of a difficult topic, but accuracy and precision are not the same thing. Errors are with populations and are not the same as residuals, which are involved in a sample. And of course, you can't handle the truth. So we substitute the mean average in as the expected or known value. That's sort of our little trick. And we don't know the truth. And a standard deviation, which is precision, is not the same as the RMSE, which is accuracy. Because RMSE has bias in it, and a standard deviation equals the RMSE when bias is removed or there's no bias. Standard deviation error, starting points for least squares. We gave you some values that you could use if you're going to do a least squares adjustment. And can't describe accuracy without stating the confidence level or how many sigma. So if nothing else, you left here knowing you can't just say I'm accurate to 1/100th of a foot. Is that 1 sigma, 2 sigma, 3 sigma? What is it? And new technology can help prevent or minimize mistakes and blunders, as long as you take into account their new accuracy and precision specifications. And as professional surveyors, we are designers, and we use error theory to prove it. I'm available to answer questions. If you end up watching this video, this is how you can reach me.